Hey, welcome back to Fat Mama Physics. In this video, I want to show you a little bit about how a uniform electric field works. So this is for SL as well as for HL. And it's important because it's also in the regular Physics 12 curriculum, and it's so I think we should probably go over this one. And it will use stuff that we've learned before. So I'm going to give you a quick recap on kind of the tools you have when you're solving for work done in a uniform electric field, and then I have a question below just to see if you can try it out yourself. So here I have a scenario. I have a uniform electric field, and usually what creates these are these positively and negatively charged plates. So we establish a potential difference across them. And since the electric field is moving towards the right, so I'll write this for field, this means that we probably have a positively charged plate on this side and a negatively charged plate on the other side. Since electric field lines go away from positive charges and towards negative charges. So here we have a positive potential. So maybe we have something like positive 100 volts set up on this side of the plate, and then maybe this side we might have, say, negative 100 volts on the other side, or something like that. Okay, so essentially we have these two plates creating this uniform electric field. So now that we have two parallel plates, the electric field here in the middle, it's because of these two parallel plates, and assume these two parallel plates kind of go on for a very long stretch of space, we can say that the electric field between the two plates is uniform, meaning that the electric field here is going to be the same as electric field here, is going to be the same there, same there, same there, etc. It doesn't, if you had to compare this to gravitational field strength, that doesn't quite work that way, because we know gravitational field strength changes the further away you move away from a mass, just like how the electric field would change the further away you move from a charged particle. So this is very different. This is, it's basically you have uniform electric field throughout. It's, imagine you're kind of, think of it as a river current. River current, assuming it's relatively all symmetric everywhere, and it's not, it doesn't change as you're going downstream. That's kind of what you're expecting. As if you put, say, if you put your boat upstream or downstream, it's going to accelerate similarly, okay? So that's the idea of a uniform electric field. Imagine a constant stream of river current, okay? So that's important to note the fact that this is a uniform electric field, meaning the electric field is the same everywhere between these two plates. So let's put that in context of a proton that I'm going to put right there. And for a proton or any positive charge, it's going to want to move with the field. That's the opposite for a negative charge, like an electron. It's going to move against the field because it wants to move again towards the positive charge. A proton, of course, is going to want to move towards the negatively charged plate. So this proton is going to want to accelerate due to this electric field, and because of that, it actually experiences an electrostatic force that is pulling it forward. And over time, it's going to accelerate, it will pick up speed, etc., as before it hits the negative end of the plate. So what about the electric potential energy? What can we say about that? If we start closer to the positive end of the plate, it's going to probably have a lot of electric potential energy because it will be able to convert that into kinetic energy. It has a lot of stored energy. So that's pretty much exactly the same as if you had a mass that is in a gravitational field. It's going to want to it'll follow the gravitational field lines. It will want to move towards whatever big mass is generating that gravitational field. Same idea with this proton here. It's going to feel a strong electropotential energy because because of its position in the electric field. it's going to want to accelerate towards the negative end of the plate. And let's say we release it from rest. It's going to have a low amounts of kinetic energy, meaning it could be 0, it could be something very low. And as it is moving across to the other side, let's say at this point, a lot of its potential energy would have been converted into kinetic energy, allowing the proton to speed up. So at this point here, it's going to have higher kinetic energy compared to what it had before, and that's because it got that from its the potential energy converting into kinetic. So here it would have lower potential energy since this is getting converted into kinetic. This potential energy getting converted to kinetic. So that's kind of the idea for a proton moving in an electric field. And since the interesting thing is that for a uniform electric field, the force is since the field is the same everywhere, the force experienced by the proton is the same everywhere. So more on that later. I just remembered that. I should have said that earlier. Okay, here we just talked about what happens when we release a proton. This is essentially, you have electric potential energy getting converted into kinetic energy, or you can say that the electric field has done work in moving this proton from A to B. Okay, sure, we can say this is A, this is point B, just for placement holders. Okay, so here the electric field here does work. Okay, this guy does work moving the proton from A to B. So here we can say the electric field did work moving the proton from A to B. So what happens if we try to take this proton and try to move it the other way? Let's say the proton started at B, and let's say we want to move it up to A. You're right, it's going to kind of go up. Remember, it's kind of like going up the river current. It's not going to be easy. Essentially, you're kind of moving against the current. So you actually have to spend some external work in moving the proton from point B to point A. And let's say you move the proton at constant speed, which means you're not going to gain any kinetic energy. So the change in kinetic energy is 0. What you have to change is the proton's electric potential energy from B to A. Since it has a higher potential energy at A, this is going to cost you positive work. So this work done to move the proton from B to A, it's going to be exactly the change in the potential energy between B and A. Okay, so this is kind of the working idea here when you're moving protons from inside a uniform electric field. So knowing that, let's talk about a few things. What if I want to find let's say I'm releasing a proton from point A, meaning that, let's set up a distance here. Let's set the distance here between A and B to be a distance of D or something. Okay, so here to here, this distance here, we'll call that D. Okay, D separation. If we want to, figure out the kinetic energy gained, or let's say the proton, was released at rest at point A, so let's write this down here. That means we know it starts off with the initial kinetic energy of 0 because it has a 0 speed, okay, since the speed is 0. And of course, we should know at this point that kinetic energy is 1/2 mv squared, okay? So the kinetic energy start off will be 0, which means that the potential energy here at A compared to the potential energy at B, this change in potential energy is going to give us the amount of energy that this proton will have. It's the amount of kinetic energy the proton will have at B. Okay, at B. To find the change in potential energy, we kind of have to think of it in terms of the amount of work done by the field. So we have to go back to this definition that by moving the proton from point A to point B. So that's going to give us that electric potential energy that we need, or the change in electric potential energy we need to see how that gets converted to kinetic, okay? So that's kind of like on the surface of the Earth, where the gravitational field is the same everywhere. You just take MGH, essentially. And that's what we want to do, but for a uniform electric field. For uniform electric field, we know that the work done is equal to the force times the distance of travel, assuming they are in the same directions. Then the other assumption here is that if we could use this one, we will have to assume that the force is constant. And that is correct. The electrostatic force acting on this proton is constant because the field is constant. We have a constant field. Just like on the surface of the Earth, the gravitational force acting on a mass is constant because we're near the surface of the Earth, where the change is insignificant. Okay, so this is why we can use Fe, the electrostatic force, times the distance, because it's all the same. Okay, so if we use Fe times d, we need to know what Fe is. What is the electrostatic force? Please don't use this one. You might be tempted to think that, oh, hey, I know this equation here, okay? But you cannot use this one because this is for charges. This is for a point charge. It's the electrostatic force between point charges, which is not the case here. Here we have an object, we have a charged particle in an electric field. So the relationship between electrostatic force and the electric field is this one, where the electrostatic force is directly dependent on the field. The stronger the field, the more force you need to move this object. So EF for field times the times the charge. Sorry, that's an E there, okay? So times the charge, and in this case will be a proton. So we can figure that one out later. But since we know Fe, substituting in the work equation, we have that the work done is equal to the electrostatic field, okay, whoopsies, E field times the charge times the distance traveled. Okay? So WEQ'd. WEQ'd. That's I don't know. Without the F, that's of course, okay? So that's how we find the work done, or the change in energy between the two locations. So let's say we want to find the speed of the proton. The speed of the proton at B, assuming it started from rest, is going to come directly from this work term, which is going to be equal to the kinetic energy, in which the kinetic energy is 1/2 mv squared. So we can go ahead and rearrange this entire equation, which here I'll use in purple. And so this is 1/2 mv squared equals to the electric field times the charge times the distance that this proton moved. Okay. So if you want to solve for v squared, then we can just go ahead and do some rearrangements. Okay, so times 2 divided by the mass, and then ultimately you're going to take the square root. But let's take this step at a time. So that gets rid of that, gets rid of that. Then we are going to be left with v squared equals to, so last but not least, take the square root, and then there we go. Okay, we get v is equal to 2EF q d over mass, and then all of that taken to the square root. Okay, so here's some interesting relationships you can look forward to. Okay, I think that's the main one I wanted to show you, because if you just move the proton against the field, that's exactly just the work done, which is the change in electric potential energy between the 2 points, which then you can just use this guy over here. Okay, so that's it. So that's kind of the gist of what that is about. here I'm going to give you a chance to try this question, haha, using all of which you've learned. So here, just give you some setup scenarios. Electron was fired with an initial speed, an electron. So this here is an electron, so be very careful. We do have an electric field, which is going towards the right, and the electric field is given here in the question. How far does this electron travel before it slows down to a stop? Woohoo! Well then, so think about this one. You might be thinking, oh, why does it slow down to a stop? I thought it's supposed to just keep accelerating. Don't forget, this is an electron, so think about this carefully. Maybe a good time to pause the video and try this question yourself. Okay, I am going to go over this question. So this is an electron, meaning that the electrostatic force acting on this electron is in the opposite direction because it wants to go against the field. So we do know that this electron starts off with an initial speed, which I'll say u, I guess, just for that matter. So that's 2.3 times 10 to the power of 5 meters per second. It's going to get shot against the field, and we want to know how far it travels before it comes to a stop. Okay, so we know that when it comes to a stop, that final velocity there has to be 0. Okay, that means if we put that means we can use that to find a change in kinetic energy. And that change in kinetic energy would be used up as this electron is gaining electric potential energy from this point to that point. So we have to do some equating there. So we know that the change in kinetic energy, which is EK, which is probably going to be EK initial, since the final is going to be 0 anyways. EK final is 0. So EK initial, which is just that one, is going to be equal to the change in the electric potential energy of this electron going up the electrostatic, going against the field, essentially. So we know that this change in potential energy is equivalent to the amount of work done. The amount of work done in taking this electron and moving it through a distance d through this electrostatic field. So this work done is equal to the constant force, the electrostatic field force being constant, times d. And we know the electrostatic force acting on any charge is the electric field, assuming that is constant, times the charge of interest. So if we put this back in over here, this is going to give us the electric field acting on this negative charge, this electron, times the electric charge, which is the elementary charge, and times the d that it is being, how far it will move up, against the current before it comes to a stop. So we have EKI is equal to the work, the change in potential energy. So let's equate these together, because we know this one is just 1/2 mu squared, Okay, so rewriting this, we get 1/2 mu squared is equal to the electric field, the electric field times Q times D. In fact, I'm not going to even worry about negative charges, because since I've worked out the direction of movement of my electron, I already know that it's going to travel some distance up it's going to move with the field. So it's actually d with the field, but for itself, it feels like it's going against the field. Okay, so we need to solve for d. Okay, so that's what we're trying to find. We don't know what d is. So solving for d, let's just move everything to the other side. EF gets moved, EQ gets moved, okay, let's move this, okay, this goes away, all right, we're going to get D is equal to 1/2 mu squared over the electric field divided by the charge. So putting everything in, we need to know the mass of an electron, which you can find in your data booklet. 9.11 times 10 to the power of -31 kilograms, very tiny. And the speed, oof, I ran out of space, so let's move this guy here. So the speed we know from given inside the question, it is 2.3 times 10 to the power 5 meters per second. This is squared, divided by the field, which I think is 2,300 Newton per Coulomb, and the charge of an electron, 1.6 times 10 to the power negative 19 coulombs. Okay, so let's put that in a calculator and see what we get. Oh, and that's not very far at all. Assuming I did my calculations correctly, this is 6.5478 times 10 to the power of negative 5 meters. Wow, that's barely any, this is like 0.06 of a millimeter. That's not very far. Okay, so to two significant figures, this is 6.5 times 10 to the power of negative 5 meters, which is, what is this? 65 micrometers. That's tiny. Okay, all right, so that's a question. I would say this is a typical question. I would highly recommend you understand the work process of this question, be able to deal with uniform fields, and the reason why the force is constant. Okay, so thank you for watching. Hopefully you learned something in this video that you can apply later. I wish you good luck, and Fat Mama Physics signing out.